Molarity. All right, now we take all of our knowledge about molecules and moles, and instead of looking at how much they weigh, we're going to take them, dissolve them in a solvent like water or some organic solvent maybe. We're going to dissolve them in a solution. Okay. And we're going to talk about concentration. So to jump into all that, let's do some definitions first of all. All right. Number one, solution. What do we mean by that? Well, a solution in chemistry is a homogeneous mixture of at least two or more substances. So remember, we mix them all together. They're not bonded, they're just mixed. They're just mixed together. They're not making new compounds, we're just mixing blue and red marbles in a bucket, right? We're just mixing them all together, and it is homogeneous. No matter where you look in that bucket, you get the same composition. There's no spots that are solid versus a gas, or one versus another substance. Alright, now your book doesn't actually show this, but I wanted to go through here. This is a table from the General Chemistry by Macquarie. I think this is useful to think about because a solution could involve any of the phases of matter. We typically think of it as the one I've highlighted here, taking a solid and dissolving it into a liquid. So like taking salt, shaking it into water, solid into a liquid, it dissolves and you get salt water, which is a solution. Okay, so sodium chloride and water is exactly the same example they use. Okay? But it doesn't have to be a solid into a liquid. You can have any kind of combination also. You could do a gas and a gas. Mix one gas into another gas, they mix together. As long as it's a homogeneous mixture, it's a solution. So air is a mixture of oxygen and nitrogen and argon and other traces of other gases. That's a homogeneous mixture. So it's a solution. Right? You could put a gas into a liquid, bubble some oxygen through water. Some of that oxygen does dissolve. I mean, it's a good thing oxygen dissolves in water. That's what the fish breathe through their gills, right? They get that oxygen out. That's a solution. Okay. They've got a gas and a solid. We don't really think about that too much, but a gas can dissolve into a solid. Their example there is hydrogen and palladium or platinum. You can actually get a homogeneous mixture of that. A liquid and a liquid. We can mix two liquids together. Water and alcohol, for example. They mix together. That's a homogeneous mixture. It's a solution. A liquid into a solid into a solid. Now there's an interesting idea. Usually what you have to do there is melt them first, get them to be liquids, mix them together, and then let them cool back off so they turn into a solid. So metal alloys, for example, brass. Brass is a mixture of two different metals, and so it's technically a solution. Alright, so going back to our more standard kind of idea of what is a solution, it is you've got some liquid solvent, you're going to dissolve some solid into it, you mix it all up, you stir it so it's homogeneous, it all dissolves, bam, you've got a solution. Now, terminology. The thing that the water or the thing that you're dissolving it into is called the solvent. The solvent. The solute is the thing that you're dissolving into it. So the salt into the water to make salt water. The salt is the solute, the water is the solvent. You put them all together, mix them, it's the solution is the whole thing. Alright, now how much salt do you put in? Do you just put like one shake, or do you dump a whole bunch of it in, alright, in the same volume? There's got to be a difference there, and sure enough, that's what we call concentration. How much do you actually put in? The concentration. Well, how do we count molecules again? We count them by moles. And how do we measure the volume? Well, liters or milliliters or something like that. Okay. So we've defined a unit in chemistry, a unit of concentration that's widely used. It's called the molarity. Based on that word, I bet it's based on moles, and sure enough, the molarity of a solution is a unit of concentration. Again, a measure of concentration. It's defined as the moles of the solute per liter of the whole solution. Alright, that's very important to remember. Moles of solute, the salt being shaken in, for example, into how much? Well, the liters, the volume in liters of the resulting solution. Okay? They don't say the liter, by the way, of the solvent. You got to be careful there. It's of the solution. So this is the volume in liters after it has dissolved. See, depending on what the solvent is and what the solute is, the volume can actually change. Sometimes it grows a little. Sometimes if the attractions between the molecules are strong, it can actually contract a little bit, right? But the volume probably does change a small amount when you put the solute in. And so be careful there. It is of the whole solution, not just the solvent. All right. Do not mix up moles, MOL, with molarity, which is abbreviated capital M. Right? Moles, MOL, is a unit of counting. Molarity, capital M, is a unit of concentration. It equals moles per liter. Very, very important. All right, so let's look at example 3.14 to help us understand this a little more. Scroll down here. 3.14, calculating molar concentrations. All right, so in other words, concentrations in terms of molarity. 355 milliliters of a soft drink contains 0.133 moles of sucrose, which is table sugar. What is the molar concentration? All right, here we go. 355 milliliters of the soft drink. Now that's the whole solution, right? 0.133 moles of sucrose. That's the solute. Right? So here I've got exactly the two things I need. I need moles on the top of the solute. They told me that, 0.133. On the bottom I need liters of the solution. Well, here's the solution, but it's 355 milliliters. That's okay. We can convert that to liters. It'd be 0.355. Put the one on the top, the other on the bottom. Here, that's what I've done here. And so I've got at the bottom here, there, sorry about that, it jumped on me. I've got 0.133 moles of the solute, sucrose, divided by 0.355 liters of the solution. Put that through your calculator, 0.375. What is the units? It's moles per liter, which again we can abbreviate as capital M, or molarity. So the molarity of that soft drink, the molarity of sucrose in that soft drink is 0.375 molar. Molar is how we would refer to that. All right, so we've got plenty of other examples here. Let's maybe take a quick look at a few of these. 315. How much sugar in moles is contained in a modest sip, 10 milliliters of the soft drink from above? This is a conversion problem, and maybe I'll work this out for you here. Let me just see. We're going to have 10 milliliters of that soft drink, and again, the concentration turned out to be 0.375. So let me go back to my scrap paper here. And let's try this. I've got a volume of 10 milliliters. That's the sip of it. And the concentration was 0.375 molar, capital M. Right, which again means 0.375 moles of sucrose. That's the solute per liter of that whole solution. All right. And I've got 10 milliliters of that solution. So I should be able to convert that to moles of sucrose, which is what they asked me. All right, now notice I've got liters on the bottom. I've got milliliters here. They're not going to cancel unless I use consistent units. So milliliters, that would be 0.010 liters of the soft drink. Let's do our conversion. Liters on the bottom, so it cancels. Moles of sucrose on the top, and my molarity tells me what that number is. 0.375 moles. Okay, 0.375 moles. That's a 7. There we go. 0.375 moles per liter. That is to say, per 1 liter. That's the same thing as 12 inches per foot. Right? That same idea. So I can use molarity, the unit of concentration, as a conversion factor. Liters cancels, top and bottom. I'll put my equal sign. 0.01 times 0.375, so that would be 0.00375 moles of sucrose. Or if I did that in scientific notation, 3.75 times 10 to the minus 3 moles of sucrose. Now, is that what they asked me for? I'm forgetting. I go back here. They said, yeah, how much sugar in terms of moles? And they got 0.004. Yeah, if I round that off, 0.004. Why did they round it off to just one significant figure? Because of the 10 here. That's what I'm starting with. 10 milliliter sip. That only has one significant figure. And so that is the correct answer. Let's round that off to 0.004 moles of sucrose. Great. Let's check out some more. Calculating molar concentrations. Let's see. Vinegar. A solution of acetic acid in water. All right, so water is my solvent. Acetic acid is my solute. It says 0.500 liter vinegar solution, so half a liter, contains 25.2 grams of acetic acid. What is the concentration in the units of molarity? I know the volume. It's 0.5 liters. That's good. To get molarity, I'm going to need the top of that fraction, which is moles of solute. The solute is acetic acid, but I don't know moles. I know 25.2 grams of acetic. I got to convert this to moles. Once I figure out how many moles of acetic acid there is, I can divide it by the volume, and then I'll have moles divided by volume, moles per liter, that is to say, which equals molarity, and that's exactly what they're asking me. So this is going to be two steps. Step one, convert 25.2 grams of acetic acid to moles. Step two, divide it by the volume to get the molarity. Alright, so let's go try this. 25.2 grams of acetic acid. Alright. 25.2 grams of acetic acid. That was CH3COOH. If I'm going to convert that to moles, I think I need to know its formula mass. That way it'll be grams per mole, and I can do that conversion. So let's go ahead and add that up. Go to my calculator. I've got 2 carbons. So 2 times 12.01 plus, I've got, looks like 4 hydrogens total. So 4 times 1.008 plus, and I've got 2 oxygens. 2 times 16.00. Alright, 60.052. That's its formula mass. 60.052 grams per mole. Great, now I can use that number to convert. I've got 25.2 grams of acetic acid. Go ahead and write that out. I want to convert that to moles. So grams on the bottom, moles on the top, and that's what I just figured out up there. 60.052 grams in 1 mole. My grams cancels. My answer will be here in moles of acetic acid. Punch that through on my calculator. Over here, 25.2 times 1 divided by 60.052. Okay, 0.4196. I'm not going to round off yet. It's always good. Don't round off in the middle of a problem. If I did right now, I'd round off to 3 sig figs because that's what 25.2 has. But you know what? Keep at least 1 or 2 extra ones here. I'm keeping 1 extra. If I want to go a little farther, I could. That'd be 6.3 out here if I want to keep, or 6.4 if I rounded 1 extra. But anyway, keep a couple extra out there and only round off at the very end of your calculation. Okay, so I've got now moles of acetic acid. And remember, the volume was 0.5 liters total. So if I want the concentration in terms of molarity of acetic acid, the concentration would be 0.41963 moles of acetic acid. Moles is on the top. Volume in liters is on the bottom. The liters is 0.500 liters, they told me. Alright, what does that equal? Go over here. I'm going to take that answer and divide it by 0.500. And so 0.839. Here I will round off to 3 significant figures because that's what I have in this problem. The unit is molarity. Moles per liter, right? Molarity. And molarity of what? Of acetic acid, so CH3COOH. There is my full final answer, 0.839 molar. And let's just see what the book came up with. Hey, don't you like it when it matches 0.839 molar? Alright, so you got to know the definition, moles of solute per liter of solution. That's what molarity is, and it's all about that. Alright, 3.17, determine the mass of the solute. Right? Very similar type calculations. I think I'll let you go through that on your own. 318, determine the volume of a solution containing a given mass. Again, very, very similar. Use the units to convert. All right. Use the units to convert, get them to cancel as usual. It's all dealing with moles of solute per liter of solution. Okay. The last thing in this section is the dilution. The dilution of solutions. To do dilution calculations, you should use the dilution formula. Here's the idea. If you have something that's more concentrated, right, and then I dilute it, which means I'm just adding the solvent. Right? So again, salt water is the solute is the salt, the sodium chloride, the solvent is the water. If I just add more water, not salt, right, then I'm diluting it. Right? There won't be as high of a concentration. I'll go from a more concentrated to a less concentrated solution because I've added water. So you see my volume, of course, goes up. But then the concentration, I use a dark green here and a light green here to show that it's thinning out. It's more dilute. It's not as concentrated. Here they got a picture from the textbook of a more concentrated solution and a less concentrated solution. Pretty blue. Probably a copper or something. Anyway, that's the idea of diluting. Right? You're adding the volume of the solvent. Right? So if you look at the before case, I have some initial concentration and some initial volume. Call it C1 and V1. After I add the solvent, then I've got some new concentration, which is lower, and some new volume, which is higher. So C2 and V2. The dilution formula is really simple. There it is. If I multiply the concentration times the volume in both cases, so C1 times V1 and C2 times V2, hey, guess what? They're going to equal each other. Why is that? That's kind of weird. Actually, it's very simple. Look what happens when I multiply concentration times volume. Concentration would be units like moles per liter. Volume is liters. My liters would cancel, and I would just get the moles of the solute. And remember, I'm not changing the moles of the solute. I'm adding the solvent only. There's just as much salt before as after. There's more water because I'm diluting it, but the amount of salt, the amount of the solute, in other words, remains the same. So yeah, it should equal. This is before, this is after. And that's why the dilution formula works. Let's do an example here. 3.19. Let's see. 3.19 says if a 0.85 liter of a 5.00 molar solution of copper nitrate is diluted to a volume of 1.8 liters. So look at, they gave me my initial numbers. The volume initial is 0.850. The concentration initial is 5.00. Right? After I diluted it, I've got a bigger volume. Now it's 1.80 liters. And they're asking me what is the molarity of that final diluted solution? What is the concentration of it? Well, initial to final, again, my initial volume, my initial concentration, my final volume, my unknown final concentration, use the dilution formula. I know what C1 is, the initial concentration, it's 5, right there. I know my initial volume is 0.85 liters. That equals C2V2. My final concentration, I don't know it. That's what I'm trying to figure out. My final volume, 1.80 liters. They told me that. And now, that's a really easy algebra problem. Solve it for C2. Concentration equals 2.36, which is what they got as well. So dilution formula, really pretty easy. I can calculate any of those. You see, C1V1 equals C2V2. Maybe they ask me for the final volume, and they give me the other three. Or maybe they ask me for the initial concentration, and they give me the other three. Right? There's going to be one that they ask for, and three that they give you, and then you can just solve for the last one. All right, we'll end this section by looking at examples 3.2 and 3.20 and 3.21. What volume of 0.12 molar HBr can be prepared from 11 milliliters of 0.45 molar HBr? Okay, so I look at this and I realize they're diluting it. They're starting off with 0.45 molar, that's the concentration initial, and they're diluting it to 0.12 molar final. So there's my C1 and my C2. My V1, 11 milliliters, or in other words 0.011 liters, that's my initial volume, V1, and they're asking me, hey, what volume? So they're asking me to calculate for V2. Alright, so C1V1, C2V2, plug it all in, turns out to be 0.041 liters, or in other words, 41 milliliters. Pretty straightforward. 3.21, volume of a concentrated solution needed for dilution. Alright, now this one might be a little trickier, so let me go through this. It says, what volume of a 1.59 molar potassium hydroxide is required? So they're asking me for V. In order to prepare 5 liters of a 0.1 molar KOH solution. Alright, so here in this case, I'm starting out with a initial more concentrated solution of 1.59 molar. I'm ended up with a dilute 0.100 molar. So it's a dilution. I'm thinking dilution formula right away. I'm trying to make 5 liters. So that's my V2. They're telling me how much I need to make, and they're telling me its final concentration. How much do I initially need? Okay. Well, let's do it. C1V1, C2V2. They gave me V2 and C2. I'm sorry, those are the... Yeah, that's right. Those are the final ones. It really doesn't matter which label 1 and 2, truthfully, but those are the final ones. Here's my initial concentration. They're plugging it all in, 0.314 liters. All right, so I was thinking they were going somewhere else with that. They didn't. It was just the dilution formula where they asked you to calculate for V1. Pretty straightforward.